Hey everyone! So today we're going to continue learning differential equations. So here's our next example. This time we have y's and x's. So let's go through our questions now. So first of all, what is the order of the differential equation? Well, I only see one derivative, and it's a first derivative on y. Therefore, it must be a first order equation. Who is the dependent and independent variables? Well, y is the dependent and x is the independent variable. Y has the derivative on it. Okay, next, is it linear? Is it nonlinear? Well, we see here a y squared term. Therefore, this is nonlinear. Remember, anything other than a first power, so a squared, a cubed, and so on, or a trig function with y, such as a sine of y or cosine of y, or if you have something that's like a y times a y prime, all nonlinear. Therefore, this is a nonlinear first order differential equation. So when we go through our list of different equations that we know how to solve, the last question that we used when we did the integrating factor, that is out. That method's gone. We can't use it here because this is nonlinear. So what's the next on our list? Next is to look to see if it's homogeneous. How can we check for that? Well, let's give a quick reminder of what it means to be a homogeneous function. Let's say we have some function that has nothing to do with this problem of x and y, which is something like x squared y plus x cubed minus y squared x. Why not? So in this case, the way you look for homogeneous functions usually is you would say, let's instead of x and y call it tx and ty. So each x gets replaced with tx, and each y gets replaced with ty. So we would have something like this. Now, we factor out all of those t's. So here we have a t squared times a t, it's a t cubed, and we're left with that. Plus this is t cubed, x cubed. This, we can pull out a t cubed, and we get a y squared x. And we see again, we can take out all of the t cubes here, and we just have x squared y plus x cubed minus y squared x. But that's what we started with. That's just t cubed times f of xy. And anytime you can pull this variable out completely, it's a homogeneous function. The power of it says that it's a homogeneous function of the third degree, but that doesn't even matter for us. All that matters is that it is homogeneous, something like this. So without going through all this work, really, what we could have done is just counted the powers. Here we had 2 powers plus 1, that's 3. Here we had a full 3, very obvious. Here we had 2 plus 1, and that's 3. And right away we could see that it's homogeneous without going through all of the full method there. So let's get rid of this. And now we're going to do the same thing for our differential equation, but what we have to remember for the equation here is that we don't count derivatives in checking this. Therefore, on the left-hand side here, we have 2 powers. We're not counting the derivative. This y, 2. And here for xy, we have 1 plus 1, 2. Therefore, this is homogeneous. They all have the same order, the same number of powers in each term, each monomial. So what does that mean? That means we've totally classified our problem now. It's a first order, nonlinear, ordinary differential equation which happens to be homogeneous. Anytime it's homogeneous, you solve it through a substitution, which is y over x. So why y over x? Well, let's divide our equation by x squared. What does it become? Y prime equals, dividing by x squared, we get a y squared over x squared plus xy divided by x squared just becomes a y over x. So if we simplify this, we see that we have a y over x all squared plus a y over x. And we see that this is a function of y over x. There's no x's by themselves, and there's no y's by themselves. It's all y over x. And then, of course, the derivative of y, but that's okay. So our substitution then makes all of the y over x's equal to u. But we have to do a little bit more. So let's rewrite our substitution here. It's y over x. We can rewrite that, though, as y equals ux. And what we want to do is take the derivative of both sides of this. We remember that y is a function of x. Therefore, on the left-hand side, it becomes y prime. On the right-hand side, it becomes now we have to use the product rule because u is also a function of x. So it becomes a u prime x plus a u. So now we have everything we need. We have what to replace y over x with and what to replace y prime with. So let's plug them all into here, our differential equation. So the left-hand side y prime becomes just u prime x plus u equals, on the right-hand side, all of the y over x's get replaced by u's. So we just get u squared plus u. So now all of the y's are gone, and we have a new differential equation, which just has u's and x's. So in a way, we have to start over and think, how do we classify this? In another way, we don't, because anytime we do this with homogeneous equations, it always gives us the same thing, which is something separable. So first, we can simplify this a little bit, right? Because we have a plus u on both sides. So subtracting u from both sides, we just get u prime x equals u squared. Now, how do we know it's separable? Well, let's write this instead as du dx. It's the same thing as u prime. X equals u squared. It's separable if you can get all of the x's to one side and all of the u's to the other side. So let's see if we can do that. What's another way to write this here? Well, we can multiply by dx. Let's go step by step. So then we would have u squared dx. We can divide by x. We would have du equals u squared dx over x. And let's divide by u squared on both sides. Then we have a du over u squared equals dx over x. Completely separable. All the variables of x are on the right-hand side. All the u's are on the left-hand side. Now, we have to integrate both sides. So let's go ahead and do that. Over here, we're going to have du over u squared. Over here, we're going to have dx over x. Let's do these integrals. So this time, they're a little easier than last time, I think. We see right away on the right-hand side, this is just a log x plus some integration constant. On the left, another way to write it, right, is just a u to the minus 2 du, and this might look a little easier now. So how can we solve that? Well, we know it's just a power law for the integrals here. We're going to add 1 to the power to make it a u to the minus 1, then divide by that minus 1. And here, normally we would add another integration constant, but because we already have one on this side, if we added another, we could just combine them into one. There's no point in having both. So we're good with just the one. And anytime you have a first order equation, you only need one constant. The number of constants should be the same as the order of the differential equation. So now at this point, we have to remember that really we didn't care about u. What we cared about was y. So maybe let's simplify this a little bit here. So we have u to the minus 1 is 1 over u, right? So this becomes a minus 1 over u is log of x plus our constant. So what was u? Well, if we remember, u was y over x. That was our initial substitution. So that means 1 over u must be x over y. So we have minus x over y equals log of x plus c. And what we want to do is solve for y. So we can do that. So we see that another way to write this is minus y over x equals, now I'm going to do 1 over this. Now to solve for y, just multiply both sides by minus x. And I get y of x equals minus x over log of x plus our constant. So we're almost done. That's our general solution. And it's general because we still have the constant. If we want to get our particular solution, we have to find out what that constant is, and in order to do that, we use our initial condition, which if we remember is y of 1 equals 1. So again, what this means is that when x is 1, y is 1. So let's plug this in here. Y of 1 equals, and we're going to replace all of the x's with 1s. 1 over log of 1 plus our constant, and this whole thing has to equal 1. So let's simplify. We have a minus 1 on top. Log of 1 is 0 plus a constant equals 1. So really we just have minus 1 over c is 1, and therefore c is minus 1. Now we have our full solution here. We're going to plug in for c. So we have y of x equals minus x over the log of x, then plus our constant, which is minus 1. And we have our full solution now to our nonlinear first order differential equation, which happened to be homogeneous.